reaction mechanisms and named reaction you may encounter in A-level chemistry exam. This is for AQA A-level chemistry. The first reaction is radical chain reaction, and you can see that in the free radical chlorination of alkanes to give you chloroalkanes. In this reaction, it starts with the initiation step where the UV light provides the energy to break the chlorine molecule into two chlorine radicals. And then the chlorine radical starts to react with the methane molecule or with the alkane to give the methyl free radical, and also the methyl free radical can react with another molecule of chlorine to give the chlorine free radical. This is called the propagation step, and this keeps the reaction going in a chain process where more and more of the free radicals are produced. Finally, termination step, where the free radicals that were produced during the propagation step react together to give you the more different molecules like chloromethane, or two methyl free radicals can react to give you ethane, or two chlorine free radicals to give you chlorine. We can also see that reaction in the CFC effect on ozone. So how exactly do CFC damage the ozone? It starts with UV light breaking the CCl bond in CFC, creating a chlorine radical. This radical is super reactive. It reacts with ozone to breaking it down into oxygen and forming ClO free radical. The cycle will continue when ClO free radical react with more of the ozone, ultimately releasing the chlorine back into the atmosphere. The overall reaction is two molecules of ozone breaking down to three molecules of oxygen. And then the chlorine here is just a catalyst which keeps continuously destroying the ozone layer. The second reaction is the nucleophilic substitution reaction, and the first reaction of that is the reaction of alkyl halides with sodium hydroxide to make alcohols. You can do this reaction by heating with aqueous sodium hydroxide. So imagine you have an alkyl halide like methyl chloride, for example, and then the OH, which is provided from the sodium hydroxide in this case, will act as a nucleophile. The OH of sodium hydroxide will attack the carbon, which is partially positive, and at the same time, the carbon-chlorine bond will break. The OH will attach itself to give you the alcohol, and then the chloride will be released, and it can give you sodium chloride as a side product. Please pay attention to the movement of the electrons, and don't forget to draw the lone pair of electrons on the nucleophile. Another example of nucleophilic substitution reaction is reaction with cyanide, and that will give you nitrile. The reaction will proceed in the exact same mechanism, where the cyanide here will be the nucleophile attacking the partially positive carbon, and the bromide will leave in this case. The reaction takes place when you reflux in ethanolic potassium cyanide. The final product will be nitrile. And also the reaction of alkyl halides with ammonia that will give you different aliphatic amines. The reaction starts also with the ammonia acting as a nucleophile under the same reaction mechanism, attacking the partially positive carbon, and the bromide will leave. But note here that the ammonia is a neutral molecule, so when it's added, it will be nitrogen will have a positive charge, but another molecule of ammonia here can act as a base and will take off one hydrogen from the nitrogen, and the electrons will be released back to the nitrogen, and that will give you the primary amine. However, the reaction will not stop at this step, because the primary amine itself can act as a nucleophile attacking another molecule of the alkyl halide, and that will give you secondary amines. And the secondary amine as well can carry on reacting as a nucleophile with the alkyl halide to give you tertiary amine, and also that will react to give you quaternary amine. This is why this type of reaction will have quite low yield if you want a specific amine, because it will give you mixture of different amines. The third reaction is the elimination reaction, and elimination reaction is basically the type of reaction that makes alkenes. With elimination reaction, you are removing elements to form double bond. That's how you make an alkene. When you heat a halogen alkene with ethanolic potassium hydroxide or sodium hydroxide, that will lead to the formation of alkene. The OH in this case, when it's ethanolic, will not act as a nucleophile, but it will act as a base. It will pull off the proton from the carbon next to the halide. So again, notice the movement of the electrons where the lone pair of electron on the OH will attack the hydrogen on the carbon next to the halide. And then the bromide or the halide will also leave, and the electrons from the hydrogen will go to make the double bond. Eventually, the product will be an alkene, water molecule, and bromide. Another example is the synthesis of alkene from alcohol, and this is called dehydration because you are removing a molecule of water. And this reaction proceeds by heating with concentrated sulfuric or phosphoric acid. These acids provide the hydrogen or a proton that acts as a catalyst for this reaction. The reaction starts with the OH on the alcohol attacking this proton from the acid. That will give you an intermediate with an oxygen that has a positive charge, and then a water molecule is going to leave in the second step. That will create a carbocation. That carbocation then will make the alkene because the hydrogen on the adjacent carbon will then give its electrons to form a double bond and will leave as a proton. So the proton here that left at the end is the same as the proton that we provided at the beginning. This is why the acid is just a catalyst for this reaction. The fourth type of reactions are the electrophilic addition reaction. And electrophilic addition reactions are reactions of alkenes. Alkenes love electrophilic addition. Take, for example, addition of hydrogen halides to alkenes. In this reaction, if you have hydrogen chloride reacting with a symmetric alkene, then the double bond of the alkene is electron rich, so it attacks the hydrogen from the hydrogen chloride, which is partially positive, and notice the movement of the electron. The chlorine will then, or the chloride will leave as a chloride with a negative charge. That will generate a carbocation where a positive charge will be generated on the other carbon where the hydrogen was not added. And then the chloride or the halide, if you use hydrogen chloride or hydrogen bromide, will then add itself to the other carbon or the carbon with the positive charge, and you end up with a halogen alkane as your product. Pay attention in case you use an unsymmetric alkenes because you're going to end up with two different products because the hydrogen will add itself to one of the two different carbons here. So when it adds itself to carbon number 2, that will give you a primary carbocation, while when it adds itself to carbon number 1, that will give you secondary carbocations. These two carbocations do not have the same stability, where the primary carbocation is less stable than the secondary carbocation, so it will form more than the primary carbocation. Then the bromide that was released from the first step will then attack the positively charged carbon in either of these two carbocations. That will give you two different products. The first one is one propane in case if we started with propene, and the other product is going to be two bromopropane. The one bromopropane will be the minor product because it formed from the less stable carbocation, while the two bromopropane will be the major product because it came from the secondary carbocation, which is the most stable or the more stable carbocation. Another example of the electrophilic addition reaction is the addition of halogens. And addition of halogens will follow the exact same mechanism. In this case, the double bond attack one of the two bromines, and then that will generate the carbocation, while the other bromine with the negative charge will then attack the carbocation to give you the dihaloalkane. In case of water or addition of water, this is called hydration, and this is used for sensors of alcohol. In this reaction, we use sulfuric acid. If you use cold sulfuric acid, then the reaction will start with the double bond on the alkene, attacking one of the hydrogen of the OH groups of the sulfuric acid. And then the electrons between the hydrogen and oxygen will move into the oxygen. That the hydrogen will will be added to the double bond, and that will generate a carbocation, as we can see here. Then the oxygen on the hydrogen sulfate ion will attack the carbon with the positive charge. That will give you an intermediate that is called the ethyl hydrogen sulfate. The ethyl hydrogen sulfate, if you warm it with water, it will hydrolyze to give you ethanol and sulfuric acid. This is the overall reaction mechanism, or the overall reaction for this one. Note that if you use unsymmetric alkene, you will end up with two products, as well as we've seen with hydrogen chloride when it was added to the alkenes. Nucleophilic addition to reaction to carbonyl group. Nucleophilic addition reaction with carbonyl compounds like aldehydes and ketones, where we have a cyanide as an example. The cyanide will attack the carbonyl carbon on the carbon double bond O here, because this is a partially positive carbon, a partially positive atom, and the oxygen will be partially negative. The cyanide has a negative charge, will attack the carbon, while the double bond will break and go into the oxygen. That will give you an intermediate now with an oxygen has a negative charge. Usually this reaction is carried by using acidified potassium cyanide. So the proton from the acid will then be added to the oxygen with the negative charge. Notice the movement of electrons from the oxygen with the negative charge with the lone pair of electron towards the proton from the acid. That will give you the final product, which is called the hydroxynitrile. Addition elimination reaction. These are the type of reaction you find with acid derivatives like acid chloride or acid anhydrides with nucleophiles. The nucleophiles that you can use here are either alcohols, amine, or water. So the reaction mechanism starts by the nucleophile attacking the carbonyl carbon of the acid chloride, and then the double bond between the carbon and oxygen breaks. Notice again the movement of the electron. This is the first step, which is the addition step. That will give you an intermediate. In this one, the oxygen will have a negative charge, and the other oxygen that comes from the alcohol that reacted, or the nucleophile, will have a positive charge. The second step will be the elimination step, where the electrons or lone pair of electrons and the negative charge on the oxygen will go to regenerate the double bond between the oxygen and carbon, and the chlorine or the chloride will leave as a leaving group in this case, and that will give you the ester. However, the ester here, the oxygen of the alcohol still has the positive charge, so we have the chloride that left from the previous step will then pull off the hydrogen from the oxygen of the alcohol that was added, and that will regenerate the oxygen with no charge, or will give you the ester with oxygen with no charge or neutral. So the final product will be an ester and hydrogen chloride. Another example you can see with the anhydride, in case you see that in your exam. So if you add an amine, if you add ammonia to an anhydride, then the reaction will follow the exact same mechanism. But here the leaving group is going to be the other carboxylate or the other part of the carboxylic acid. And then eventually you're going to end up with an amide and ammonium carboxylate, or if you use, in this case, ethanoic acid, it's going to be ammonium ethanoate. Esterification is how acids and alcohols form ester. So in esterification, this is acids and alcohol combined together to make esters. The alcohol oxygen will attack also the carbonyl carbon of the acid, and then a water molecule will be removed, resulting in the formation of different esters depending on the alcohol and the acid we use. We normally use an acid as a catalyst for these type of reactions. And then hydrolysis, which is breaking esters into alcohols. In hydrolysis, the reverse will happen, where water molecules breaks the ester bond. We have two types of hydrolysis, either the acid catalyzed hydrolysis, which will be the complete opposite for the esterification reaction, where we use an acid as a catalyst in presence of water to break down the ester into an acid and alcohol. Or we can use the base catalyzed hydrolysis, hydrolysis, will you use a base like sodium hydroxide or potassium hydroxide under reflux, and the OH is the nucleophile that will attack the carbonyl carbon in this case, and then that will give you the salt of the carboxylic acid and then the alcohol. Saponification is basically making soap, or which is a type of base catalyzed hydrolysis. You can take a fat, right, like triglycerides, and react it with a strong base like sodium hydroxide. The ester bond in the fat will break down. This is the ester bond, and it will break down to give you glycerol, and it will give you the fatty sodium salt of the fatty acid. This is what we call the soap, and this is why soap molecule have hydrophobic tail and hydrophilic head. The hydrophilic head comes from this part, which is the salt, and the hydrophobic tail is this long chain fat or long chain carboxylic acid. Electrophilic substitution reaction. These are the type of reaction we find with the benzene ring. There are two types of electrophilic substitution reaction. The first one is the Friedel-Crafts acylation. In Friedel-Crafts acylation, in this reaction, we produce the asylum ion. We produce the asylum ion. This is the electrophile that's going to be attacked by the benzene ring, and it's generated using the aluminum chloride when we reacted with acid chloride. So the reaction between acid chloride and aluminum chloride will give you the asylum ion. This asylum ion then will be attacked by the electrons from inside the benzene ring, and that will open the ring of the electrons inside the benzene, creating a carbocation. And then the next step is that the hydrogen that will be removed and as a proton, and the electrons will go back inside the benzene ring to regenerate the aromatic system or the full electron ring inside the benzene ring. And then the final product will be the acyl benzene. The next electrophilic substitution reaction is the nitration. So when you warm benzene with conc nitric and sulfuric acid, well, that will give you nitrobenzene. The sulfuric acid will act as a catalyst to make the nitronium ion, which is the electrophile in this case. This is the nitronium ion, which is going to act as a nucleophile. The reaction mechanism will be exactly the same like the one in the Friedel-Crafts acylation, where in this case the electrons will go from the movement of electrons will go from the electrons inside the ring towards the asylum ion, and that will break the electron continuity of the electron ring inside, creating a carbocation, and then the hydrogen will leave as a proton, and the electrons will go back inside the ring, doing a substitution reaction, electrophilic substitution, forming nitrobenzene. If you keep the temperature below 55 degrees, that will get you mono-substituted nitrobenzene. The last set of reactions are the reduction, and we have three different reduction reactions. Basically, reduction here will be addition of hydrogen. The first one is the reduction of cyanide to make amines. We have two types of reaction. The first one, when you use lithium aluminum hydride and then dilute acid to reduce the cyanide and make primary amine. There is also when you use a nickel catalyst in presence of hydrogen gas at high temperature and pressure, that will also give you primary amine. These reactions are preferred over the nucleophilic substitution reaction of alkyl halides with ammonia, because you only get one product, not a mixture of products like primary, secondary, and tertiary amines. And then we have the reduction of the aromatic nitro compounds to form aromatic amine. In this case, we use tin and conc hydrochloric acid and reflux, and then we use sodium hydroxide. That will give you the aromatic amine, which is phenylamine. This method is widely used in producing aniline, which is a key intermediate in making dyes and pharmaceuticals.